Advanced functions, section 6.1, radian measure, and I specifically chose like a globe picture here, and you'll see why I have this background. So what is a radian? So don't look at the definition yet. We're going to look at this circle. We've got a circle and we've got a radius right here. This red line is a radius of some length. So the radius is marked in red, and then we take that same length and curve it along the side of the circle. That's now an arc length. Now that length here is the same as this piece here. Let me label all of that. So the original radius was r, but this arc length is also r. So then once we had those two pieces, we drew another r here, we drew another line back to the circle, and we have a segment, we have a sector of a circle here with an angle in the middle, and that green angle is really important, that green piece in the middle. That is a radian. Anytime you draw a circle, so even if I draw a tiny little circle over here, I draw a little circle, and then I put in a radius, right? There's a radius. And then I take that exact same short little red length and I curve it around the arc here a little bit. If I could match it exactly, which I'm not using a computer, so it's not a great job there. If that were the same length, and then I drew another radius down from there, the little green segment in the middle here, that is a radian. So if I measured both of those green angles right now, they would be exactly the same in degrees, if I measured them in degrees, right? Let's say it's about 60 degrees. It's not. We will find out later exactly what it is, but it looks like it's about 60 degrees. So no matter what size of circle I draw, if I can put all those proportions in there properly, those radians, if I can draw a radii here, the same, all these, so plural of radius is radii. So I've got a radii here and here, and I've got the same length here. This angle will always be the same, no matter what size of circle I draw. A radian is the size of an angle that is subtended at the center of a circle. That just means that I've got this arc here, that is the endpoints of this. So this arc is equal length of the radius. So anytime you can draw something like this, this angle measurement is going to be a radian. You think of how we measure all kinds of things. We measure lengths in centimeters or in inches. You have two ways of measuring length, and we have to convert between them all the time, centimeters to inches, inches to centimeters, but they both measure length. Measuring temperature, Fahrenheit or Celsius, you convert between them all the time. There are two different ways of measuring temperature. So this is the same idea that we're talking about today. We have degrees and we have radians, are both ways of measuring angles or rotations around a circle. So I'm going to show you a video, Khan Academy video, because he's great, and it's going to explain in more detail what a radian is. Before you do that, I want you to read this part here. So press pause and read this. Make sure your calculator is set up into radian mode for what we're going to do today, and then we'll move on to the next slide.
You are by now probably used to the idea of measuring angles in degrees. We use it in everyday language. We've done some examples on this playlist where if you had an angle like that, you might call that a 30 degree angle. If you have an angle like this, you could call that a 90 degree angle, and we'd often use this symbol just like that. If you were to go 180 degrees, you'd essentially form a straight line. Make these proper angles. If you go 360 degrees, you have essentially done one full rotation. And if you watch figure skating on the Olympics and someone does a rotation, they'll say, oh, they did a 360, or especially in some skateboarding competitions and things like that. But the one thing to realize, and it might not be obvious right from the get-go, but this whole notion of degrees, this is a human constructed system. This is not the only way that you can measure angles. And if you think about it, you're saying, well, why do we call a full rotation 360 degrees? And there are some possible theories, and I encourage you to think about them. Why does 360 degrees show up in our culture as a full rotation? Well, there's a couple of theories there. One is ancient calendars, and even our calendar is close to this, but ancient calendars were based on 360 days in a year. Some ancient astronomers observed that things seemed to move 1/360th of the sky or per day. Another theory is the ancient Babylonians liked equilateral triangles a lot, and they had a base 60 number system, so they had 60 symbols. We only have 10. We have a base 10, they had 60. So in our system, we like to divide things into 10. They probably like to divide things into 60. So if you had a circle and you divided it into about 6 equilateral triangles, and each of those equilateral triangles you divided into 60 sections because you have a base 60 number system, then you might end up with 360 degrees. What I want to think about in this video is an alternate way of measuring angles. And that alternate way, even though it might not seem as intuitive to you from the get-go, in some ways is much more mathematically pure than degrees. It's not based on these cultural artifacts of base 60 number systems or astronomical patterns. To some degree, an alien on another planet would not use degrees, especially if the degrees are motivated by these astronomical phenomena, but they might use what we're going to define as a radian. There's a certain degree of purity here. Radians. So let's just cut to the chase and define what a radian is. So let me draw a circle here. My best attempt at drawing a circle. Not bad. And let me draw the center of the circle. And now let me draw this radius. And let's say that this radius, you might already notice the word radius is very close to the word radians, and that's not a coincidence. So let's say that this radius, the circle has a radius of length r. Now let's construct an angle. I'll call that angle theta. So let's construct an angle theta. So let's call this angle right over here theta. And let's just say, for the sake of argument, that this angle is just the exact right measure, so that if you look at the arc that subtends this angle, that seems like a very fancy word. Let me draw the angle. So if you were to draw the angle, so if you look at the arc that subtends the angle, that's a fancy word. That's really just talking about the arc along the circle that intersects the two sides of the angles. So this arc right over here subtends angle, the angle theta. So let me write that down. Subtends, this arc subtends angle theta. Let's say theta is the exact right size, so that this arc is also the same length as the radius of the circle. So this arc is also of length r. So given that, if you were defining a new type of angle measurement, and you wanted to call it a radian, which is very close to a radius, how many radians would you define this angle to be? Well, the most obvious one, if you kind of view a radian as another way of saying radiuses, or I guess radii, well, you say, look, this is subtended by an arc of 1 radius, so why don't we call this right over here 1 radian? Why don't we call this 1 radian? Which is exactly how a radian is defined. When you have a circle and you have an angle of 1 radian, the arc that subtends it is exactly 1 radius long, which you can imagine might be a little bit useful as we start to interpret more and more types of circles. When you give it degrees, you have to do a little bit of math and think about the circumference and all of that to think about how many radiuses are subtending that angle. Here, the angle in radians tells you exactly the arc length that is subtending the angle. So let's do a couple of thought experiments here. So given that, what would be the angle in radians if we were to go, so let me draw another circle here. So let me draw another circle here. So that's the center, and we'll start right over there. So what would happen if I had an angle, if I wanted to measure in radians, what angle would this be in radians? And you can almost think of it as radiuses. So what would that angle be? Going 1 full revolution, and in degrees, that would be 360 degrees. Based on this definition, what would this be in radians? Well, let's think about the arc that subtends this angle. The arc that subtends this angle is the entire circumference of this circle. It's the entire circumference. It's the entire circumference of this circle. Well, what's the circumference of a circle in terms of radiuses? So if this has length r, if the radius is length r, what's the circumference of the circle in terms of r? Well, we know that. That's going to be 2 pi r. 2 pi r. So going back to this angle, what's the length of the arc that subtends this angle is how many radiuses this is? What's 2 pi radiuses? It's 2 pi times r. So this angle right over here, this angle, I'll call this a different, let's call this angle x. X in this case is going to be 2 pi radians. And it is subtended by an arc length of 2 pi radiuses. If the radius was 1 unit, then this would be 2 pi times 1, 2 pi radiuses. So given that, let's start to think about how we can convert between radians and degrees and vice versa. If I were to have, and we can just follow up over here, if we do 1 full revolution, that is 2 pi radians, 2 pi radians. How many degrees is this going to be equal to? Well, we already know this. A full revolution in degrees is 360 degrees. Is 360, well, I could either write out the word degrees or I can use this little degree notation there. Actually, let me write out the word degrees. It might make things a little bit clearer that we're kind of using units in both cases. Now, if we wanted to simplify this a little bit, we could divide both sides by 2, in which case we would get on the left-hand side, we would get pi radians would be equal to how many degrees? Well, it would be equal to 180 degrees. 180 degrees. And I could write it that way, or I could write it that way. And you see over here, this is 180 degrees. And you also see, if you were to draw a circle around here, we've gone halfway around the circle. So the arc length, or the arc that subtends the angle, is half the circumference. Half the circumference are pi radiuses. So we call this pi radians. Pi radians is 180 degrees. And from this, we can come up with conversions. So 1 radian would be how many degrees? Well, to do that, we would just have to divide both sides by pi. And on the left-hand side, you'd be left with 1, I'll just write it singular now, 1 radian is equal to, I'm just dividing both sides. Let me make it clear what I'm doing here, just to show you this isn't some voodoo. So I'm just dividing both sides by pi here. On the left-hand side, you're left with 1, and on the right-hand side, you're left with 180 over pi degrees. So 1 radian is equal to 180 over pi degrees, which is starting to make it an interesting way to convert them. Let's think about it the other way. If I were to have 1 degree, how many radians is that? Well, let's start off with, let me rewrite this thing over here. We said pi radians is equal to 180 degrees. 180 degrees. So now we want to think about 1 degree. So let's solve for 1 degree. 1 degree, we can divide both sides by 180. We are left with pi over 180 radians is equal to 1 degree. So pi over 180 radians is equal to 1 degree. This might seem confusing and daunting, and it was for me the first time I was exposed to it, especially because we're not exposed to this in our everyday life. But what we're going to see over the next few examples is that as long as we keep in mind this whole idea that 2 pi radians is equal to 360 degrees, or that pi radians is equal to 180 degrees, which is the two things that I do keep in my mind, we can always rederive these two things. You might say, hey, how do I remember if it's pi over 180 or 180 over pi to convert the two things? Well, just remember, which is hopefully intuitive, that 2 pi radians is equal to 360 degrees. And we'll work through a bunch of examples in the next video to just make sure that we're used to converting one way or the other.
So here's a bit of a summary of what we learned from that video, that you probably have written down all these important factual points about what radians and degrees are and how they convert. And let's use an example here to illustrate that. We're going to convert each angle from degrees to radians in exact forms. We've got 82 degrees. Let's get an idea first of what 82 degrees means. Let me draw a little circle here. 82 degrees would be, if this is this, if I was measuring 82 degrees, that might be, maybe this would be 82 degrees. Well, that's probably not right, but let's say that's 82 degrees right in there. So I want to know in radians, how much is that? So measuring that in radians. So what I have to do to convert is I want to multiply by 1. Remember that great mathematical strategy to multiply by 1, because I want to get out of degrees. So I look at my 4 options here, and my 1, I'm choosing this one right here. 1 degree is equal to pi over 180. And why am I choosing the second one and not the first one? Well, that's because I want to be able to cancel out degrees and work with radians. So now, since I have a degree in the numerator and the degree in the denominator, they'll cancel out with each other. The question says in exact form, so I'm not going to change pi to 3.14. I'm going to leave pi as pi. But I can divide both of these numbers by 2 to reduce them a little bit. That will give me a 41 in the numerator and 90 in the denominator. So I write that as 41 pi over 90. So that answer is in radians. Now you don't need to put, I'm just showing you here, but you don't need to write radians there. This answer is now in radians because I have a pi in it. Let's try another one, 360 degrees. How many radians is 360 degrees? So again, we're going to get, we want to convert it. We have to multiply by pi over 180, which is equal to 1. So I'm going to cancel out the degree symbols, and then I'm going to reduce the 360 and the 180. 360 over 180 is simply 2. So we have 2 pi radians. So 360 degrees is 2 pi. That's one important one. 360 is 2 pi. The one on the top right here gives us pi is 180, so obviously 2 pi is 360. Those two are equivalent. This is one that I have memorized, and then I just use it all the time whenever I'm trying to convert. C says 195 degrees, so I'm going to multiply that by 1. I'm going to get rid of my degree symbol. Now, just to show you, in case you don't know how to use the fraction button on your calculator, the fraction button on your calculator, it might look like this, A, B over C. That might be the button there. Or it might be D over C, something like that. So if you put into your calculator, if you type 195, and then you use whatever your fraction button is, A, B, C, something like that, you put that button, and then 180, it will reduce it for you. And you'll see kind of, sometimes it's an L or a backwards L in there. So your calculator might now be showing you something like 1 and 1/12 would look like this. Or it might have some different symbol here instead of an L. We want it as an improper fraction, so you might have to hit your shift key or your second function to get it to switch to improper. And that should be 13 over 12. And don't forget about pi, because now we're in radians. And we can put that in the numerator or we can put that in the middle, but we don't put it in the denominator. So let's go the other way. Convert each radian measure to degrees. 4 pi over 3, I want to get out of radians and into degrees. So I have to multiply by 1, and here's my 1 this time. Notice I have the pi in the denominator this time because what I want to do is cancel this pi with this pi. So my radians are now gone, and I'm bringing in the degrees. Again, you can use your calculator. You could do 4 times 180 and then divide by 3, or you can cancel your 180 and your 3. You're going to get 240. Don't forget the units. This one is in degrees. 1.26 radians. So this one's a little different because it doesn't have a pi in it, but it has the word radians to tell you that we're in radians because the pi isn't there to indicate that. And there's decimals. So if there's decimals, then we are going to, instead of using just pi, we will use 3.1459. We're going to use the number for pi as much as we can. So we still multiply by 1 because we want to get rid of radians. And the next step now is to do 1.26 times 180, divide by, if you have a pi button, use your pi button. If you don't, well, you should get a new calculator. Don't just type in 3.14, use your pi button. And we're going to get approximately 72.2 degrees here. Next one is 1 radian. That's an important one. What is 1 radian? So 1 radian, let me show you the visual of that again. 1 radian is, remember from what we've already learned today, 1 radian is if I draw a radius here in this circle, that's a radius, and I use the same length to go up along the arc here, if that's also the same length, I can call that R, that arc length. Turn that into an angle, and the angle in here is called a radian. So how many degrees is 1 radian? That's what we're converting to here. So let's multiply by 1, and our radians are gone. And on your calculator, you're going to do 180 divided by pi, and you get 57.3 degrees. So 1 radian will always be, that angle is always going to be about 57.3 degrees. Next slide. Back to a little definition again. Here's theta, here's an angle. An angle is 1, in this case it's 1 radian because we have our radius length here on both sides, those are equal to each other. And this arc length for this diagram is equal to a radian, is equal to a radius. So this is another example of what a radian is. And we're going to use this formula, theta equals arc length divided by r, when we're looking for the subtended angle, because it's not always going to be 1 radian. So we need a formula for that. A word problem. Determine the arc length of a circle with a radius of 15 if the central angle is 2.8. Notice there are no units here. So let's get a little idea of what we're talking about, and we're going to put our answer in centimeters. So let me just draw a little circle here. I'll put it up under beside the top circle on the top right. So here's a circle for our question. We've got a radius of 15. Let's put that in there. There's 15 for the radius. And we want to find the arc length of a circle with a radius of 15 and a central angle of 2.8. Okay, central angle of 2.8. So that would be in radians. That would be our angle. So let me just, I'm going to do a little guess here, right? Because I'm not that comfortable with radians. I don't really know what 2.8 means. So let's just put an angle out here somewhere. Let's say that's 2.8. That's our 2.8. This is our central angle. So that's theta is an angle, and it's going to be 2.8. So we're not talking about degrees. We're talking about radians now. And the question is asking us for the arc length. This is the arc length here. This is what we're trying to find out. What is that length given this information? So let's use our formula. Our formula that is in the box on the top left for part A. Part A. Theta equals arc length divided by radius. So we're going to sub in here. Our theta is our angle, and that's 2.8. That's equal to our arc length is what we're trying to find out, and the radius is 15. So just using your calculator, we get an arc length, A equals 42. So that's what the arc length is in centimeters, and we'll just put a little sentence there. And I'm going to just put it up here in the circle too, 42 centimeters. So that was pretty straightforward. It's just a formula we're subbing into, and it's helping us to make sense of our new measurement. Next part, B. What if the central angle was 75 degrees? Okay, so we have a different piece of the information here. If the central angle was 75 degrees, 75 degrees, that formula in the box on the top left only works for radians, okay? I can't use that for degrees, so I'm going to have to convert to radians. And we just did a bunch of examples like that. We're going to convert 75 degrees to radians, so we do 75 degrees times 1. We want the same unit in the denominator that's in the original question, so they'll cancel. So these units are going to cancel out here. And we're going to keep it in exact form, 5 pi over 12. So that's the same as 75 degrees. 75 degrees equals 5 pi over 12. Now you could put in your 3.14 for pi to get a number answer if you're more comfortable with that, but we're going to leave it in exact form, and pi is pi. You'll get more comfortable with pi as we go on through the unit. So now we can go to our formula. Theta equals arc length divided by radius equals. So I'm going to sub in, theta is 5 pi over 12. My arc length is my unknown, and my radius is 15. So I'm just going to multiply the 15 up to the numerator here so that a will be isolated. So on the right side, I'm just going to have a. And when 15 times 5 over 12 reduces a little bit to 25 pi over 4. So we'll have a sentence to go with that. And I'm actually going to put my answer in decimals as well, just so that we can have the exact answer and the approximate answer. So our arc length is about 19.6 centimeters. Our next slide is probably the most complicated of what we're doing today. The Greek letter omega is written as a capital letter like this, and lowercase like this. Looks like a W, but it's omega. Omega is the last letter of the alphabet. And the word alphabet, of course, comes from the first two letters, alpha, beta. That's why we have our word alphabet. In physics, the lowercase omega is used to represent angular velocity or rotational speed. We have a water wheel with a diameter of 8 meters. So I looked for a picture, and I don't think this diameter is 8 meters, but I wanted to give you a visual of what a water wheel is. We're going to find the angular velocity in radians per second of a nail head on the outer circumference. So somewhere on the outer circumference of this water wheel there is a nail, and it's spinning around as the water wheel is spinning around. And we want to find the angular velocity, so like the speed that it's rotating around. Now this wheel makes 100 revolutions in 1 minute, so it's pretty fast to moving 100 revolutions in 1 minute. So we're just going to look at part A right now. We'll do part B later. We have a formula for the omega, which is our angular velocity, is equal to theta. Now you know theta means angle, whether it's, in this case it's in radians, but in radians or degrees, theta means angle, over time. Angular velocity expressed in this form, revolutions per minute or radians per second. The question wants us to find it radians per second. So notice that they gave us 100 revolutions per minute. So we were given the angular velocity in revolutions per minute, but we want it to be in radians per second. So this is just really a conversion question here. This is about converting from one form to another form. So I'm just going to write it as a proper fraction instead of this per, you know, all on one line. So there's your 100 revolutions per minute. Now I need to change that to radians per second. The question says you need to find it in radians per second. So once again, converting, we multiply by 1. Look at all these ones I have for you down here. These are all equal to 1, all of these things here, and there's more. So let's take, for example, 360 degrees. 360 degrees is 1 revolution of anything, right? Going around anything circular, 360 degrees, that's 1 revolution. I could also flip it over and write it the other way. I could write 1 revolution on the top is equal to 360 degrees on the bottom. So all these can be flipped over. 1 revolution is also equal to 2 pi. 2 pi is also equal to 360 degrees. So for these first 3 are all the same. I just use them in different combinations. So we want to go from revolutions per minute to radians per second. So let's talk about time first. How am I going to get away from minutes and into seconds? I'm going to multiply by 1. So that's what my 1 is going to look like. 1 minute is equal to 60 seconds. And the reason that I'm doing this is so that I can cancel my minutes. The minutes are gone. So when you multiply by 1, they have to be diagonally opposite to each other. You can only cancel numerator to denominator. So I couldn't use this one down here at the bottom because, well, I'm using this, but I flipped it over because I have to be able to cancel. So right now I've got 100 revolutions per 60 seconds. So that's good. I'm partway there. I've got the seconds done. Now I've got to get out of revolutions and into radians. So what can I put in my denominator so that I can cancel the revolutions? I'm going to multiply by 2 pi over 1 revolution because that way I get rid of the revolutions and I've got my radians in there now. So we put all of that together. So let me just write it out here. Omega is equal to what's left. I've got a 100 in the numerator. I've got this 1, which I'm not going to write out, and then I've got a 2 pi. So 100 times 2 pi, that's what I've got left in my numerator. And the only thing left in the denominator is 60 seconds. 60 seconds. So we've got everything all together. Now we just have to reduce fractions. So our numerator would be 200 pi over 60. That's going to reduce to 10 pi over 3. And our units, so the pi tells us that we're in radians. And then the units on the denominator is seconds, and that's what the question asked for. Radians per second. So we've got radians per second. An exact answer would be approximately 10.47 radians per second. So that's part A. That one was just an exercise in conversion. Part B is harder. How far has a nail head traveled in 5 minutes? How far has it traveled? Okay, so we're not talking about it's gone, that it's fallen off, the water wheel's fallen off the axle here and it's rolling down the street. It's how far has it gone around, and all it's done is gone around and around and around and around, but total distance traveled, so it's going around and around how many times. That's what we're going to try to figure out. How far has it traveled in 5 minutes? We're going to solve it 2 different ways. So there's kind of a longer way and a shorter way, but I'm going to start with the longer way, and we're going to put our answer in exact and approximate, just like we did down here. So version 1. Let's figure out the total revolutions first of all. The total revolutions that this nail head traveled in 5 minutes. So remember that we've got 100 revolutions per minute. So it's doing 100 revolutions per minute, and it's doing that for 5 minutes. So that means the total revolutions for part B is 500 revolutions. The nail head went around here 500 times in 5 minutes. Okay, next thing we want to talk about is the units. So we don't want our answer in units. We're going to convert revolutions. We don't want our answer in revolutions. We want to convert it to radians. Convert to radians. So 500 revolutions. How am I going to convert that to radians? Conversion. Look at that box in the bottom left. So my angle, theta, instead of saying it's in revolutions, we want to convert it to radians. So I have to have revolutions on the denominator so that I can cancel these two revolutions. And 1 revolution is equal to 2 pi, right? That's equal to 1 right there. 1 revolution is equal to 2 pi. So let me cancel off the revolutions there. That leaves us with 1,000 pi. So that is the angle in radians, as opposed to in revolutions or in degrees. Theta is 1,000 pi. Now we need to find the distance traveled. So we go back to our little formula from the previous example, distance traveled. We need radians, remember, for this formula. So I'm going to put in here our theta. We just figured out our theta. Theta is 1,000. I'm running out of room here. 1,000 pi. Arc length, that's what I don't know. The arc length is going to tell me the distance traveled. That's the arc length. So the arc length is the distance traveled. My radius, what's the radius? We haven't really talked about this yet. What is the radius? Look right up to the top of example 4. It has a diameter of 8 meters. So the radius is 4. So I get an arc length. I'll put it right here. My arc length is 4,000 pi. That's an exact answer. 4,000 pi. So we're going to do this all again. That's why I'm crowding my answer in here, because I want to put 2 versions here. So I've got an arc length of 4,000 pi. It's exact and approximate. So you're also going to get out your calculator and do 4,000 times pi. So we'll have 2 answers, but we'll put our sentence when we're done both versions here. So right now we've got our distance traveled by the nail head in 5 minutes is 4,000 pi meters. I'll put a little m there. We've got meters. Meters. Okay, so that's one way to get our answer, and I'll do a sentence when I'm done version 2. Version 2 is a little bit different. So version 2 is faster, I think. Version 2 just goes back to our circumference. Circumference is equal to pi times diameter. So my circumference is equal to pi, and my diameter, we know, we just figured that out, is 8. Let me just write it out like this. Circumference equals 8 pi. So let's think about something else for a second. Remember, over here, we already figured out that the nail head does 500 revolutions in 5 minutes, goes around 500 times. So 500 revolutions means, okay, looking up at the picture here, 500 revolutions means it's going around this circle 500 times. It's going around and around and around and around 500 times. That means whatever our circumference is, it's going around the circumference 500 times. So I've got to take 500 and I've got to multiply that by the circumference. That will be the same as 500. Got to do the same thing to both sides. 500 times 8 pi. So I'm multiplying both sides by 500 because it's going around 500 times, not one circumference. One circumference is 8 pi, but I've got 500 of them, so I'm going to multiply everything by 500. So 500 circumferences is equal to 500 times 8, same answer, 4,000 pi meters. So that's the same answer we got, maybe a little less complicated. I'm just going to put a sentence down for that. Therefore, the total distance traveled in 5 minutes is 4,000 pi meters, or approximately 12,566.37 meters. So that's the end of this problem. When you're doing questions on your own, it's always good to go back and review what you have learned, because you'll see similar strategies here and what is needed for the homework. Good luck.